So we now want to discuss what are line integrals of vector fields. I want to briefly remind you what are vector fields. Vector fields are just functions, okay, functions, let's say of two variables, which as their output don't give a scalar, but rather give a vector. So we denote them with an arrow, and usually we're going to use capital letters for vector fields. So for example, suppose we have a function f, which is p of xy, this is now a scalar function, in the I direction, plus q of xy in the j direction. So at any point xy, f gives you some number in the I direction, p of xy, plus some number in the j direction. It gives out a vector. We've seen examples of vector fields. Okay, so f is a vector field. It's a vector function, but the usual terminology is to call it a field. It's a function that goes from R2 to R2, or from R3 to R3. That could also be the case. We're going to discuss line integrals first for functions of two variables, but we can do it for three variables just as well. And an example, what is the vector field that we've been handling so far, that we have discussed at length? You should just make that connection and say, hey, that was a vector field. Do you remember? Dun, 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 dun. The gradient of a scalar function. This was a vector field. At any point xy, so if little f is a scalar function, the gradient of f is a vector function. Its components are the derivative of f with respect to x in the I direction, and the derivative of f with respect to y in the j direction. Do you see that the gradient is a field? Do you see that? Clear? And why are they called fields? And why do we think of them as fields? Because at every point xy, we don't just get a number, we get a little arrow. Okay, and if the field is continuous, then at nearby points, it's going to look like this. And if you're thinking wheat, for example, or grass, or whatever, do you see the field? Okay, good. And many things in physics, so this is how we kind of draw vector fields. We can't draw the actual graph or anything of that sort because it's a function from R2 to R2. We need 4 dimensions, right? So no hope of drawing this in an accurate way. We can only either draw the image at every point, we have this little arrow or something like that. This is kind of a way to think of it. Okay? Now, in physics, for example, many things are vector fields. For example, force is a field. Okay? The electromagnetic field is a field. Okay? So many things are fields, and that's the motivation for studying vector fields and doing line integrals and surface integrals and lots of important theorems that we're going to have coming up on vector fields. So in fact, vector fields are going to be the main topic that we're going to study from now until the end of the course. Okay, so we're going to assume, so f is going to be f of xy equals p of xy. Q of xy is going to be a vector field. And we're going to assume that as a field, it belongs to C1, meaning it has continuous partial derivatives. Remember what C1 means? And that means for f, it means that both of the functions that are the components have continuous partial derivatives. Okay? So when we're discussing partial derivatives of f, there are 4 of them here. There are the 2 derivatives of p and the 2 derivatives of q. Okay? And all of them we're assuming to be continuous. Okay? So that's what it means belonging to C1. And we have a curve. Here's the curve. gamma, and F is defined somewhere in space. In fact, it could have an R component. Let's throw in the R now, just so the picture. At every point on the curve, F gives you some arrow, right? Now I made a total mess. Do you see that I made a total mess? I wanted to say it's f of x, y, z now. Okay, let's leave it in 2 dimensions. If I wanna make it a field from R3 to R3, then it's gonna have to be an f of x, y, z, and there's gonna be p of x, y, z, q of x, y, z, r of x, y, z, in the 3 directions, I, j, and k. Okay. Let's just write it like this for now. So at every point along the curve, F gives you some arrow, right? That's the meaning of a field. At every point. Okay? Now suppose, for motivation, suppose that F is work. Okay? Sorry, F is a force. Okay, so assume this is motivation, and this is not just motivation, this is the motivation. This is the most standard interpretation of a field integral, of a line integral of vector fields. So motivation, the motivation. Assume F is a force, some force. And gamma is a curve, and we want to know the work done by the force along the curve gamma. What is the work? What is the work done by F along gamma? So suppose there's this little bead here, and the force is moving this bead along gamma from one side to the other side. How much work is the force doing? So in general, the way work relates to force is the following. In general, so for a constant force, if F is a constant force, then the work equals the force times the displacement, the distance that the force operated on. So work equals force times, bless you, displacement, the distance. Okay, do you all know this? Okay. But the interesting question is when F is not constant. F is some f of xy, and at every point it's given differently. For example, the force of an electromagnetic field. Okay, at every point it could be something different. So if F is fxy, so it's not constant, what do we get? So let's go back to, or let's draw the picture again. Suppose this is part of gamma, and this is the force at this point here. Well, what we're going to do is we're going to break gamma into little segments. In each segment, approximate the force by just taking the force at some intermediate point, and then doing a Riemann sum, and in the limit we're going to get an integral. Do you see the overall idea that's kind of become routine here in these sort of arguments? But there's a preliminary thing that we have to do. The force at every point is not necessarily doing work. So only the component of the force in the direction of the tangent is actually doing work. If the force was, let's say, pointing in this direction, it would not be able to move the bead at all. Do you agree? The bead is on the wire. The bead cannot suddenly jump in this direction. Okay? So if the force is pointing in this direction, in perpendicular to the wire, it would not be doing work at all, right? So the force, the component of the force that is actually doing work is the component of the force in the direction of the tangent. Do you see that? Do you agree to that? So here's the tangent. Let's take the normalized tangent. We denoted it previously by capital T. So this is the tangent vector of length 1, a normalized tangent. And the component, so let's write, this we'll do in a second. The component of f, which is, let's say, doing the work, is the component in the direction of t, which is f dot t. Right? Their scalar product is precisely the projection of one onto the other. Remember that we said that? So f dot t, let's just rewrite it. It's the length of f times the length of t. What's the length of t? 1 times cosine of the angle between them, theta. Okay, so this is just 1, so it's the length of f times cosine theta. This is the component of f that's actually doing work. Do you agree? Okay. Therefore, for a non-constant f, for fxy, what is the total work? So we're going to break the wire into small little segments. What's going to be the length of each little segment like this? Delta SI, right? Where S is the arc length variable. So from SI minus 1 to SI, it's going to be delta SI. And on each little segment like this, the contribution, the work that it contributes to the entire thing is the displacement, delta SI, times the force. Or at least the component of the force that actually does work, which is F cosine theta, or F dot T. Okay? So the total work is, and let's move to this work, W, approximated by the sum over all these little segments, F dot T, which is the component of the force that actually does the work, times the displacement. Do you agree? This is the approximation. As we take the limit and make these delta SI smaller and smaller and smaller and smaller, what we're going to get, this is again, it's a Riemann sum, right? It's the sum of the values at some intermediate. I didn't write here x of SI, y of SI, and t at that point, and so on. I just wrote it. This is not the completely formal writing. So as we refine the partition, we get the integral from 0 to L ds of f dot t rather than just f itself. And note that this is a scalar, right? It's the dot product of two vectors. This is a scalar. This is a regular scalar function line integral. This is something we know. Okay? This is a line integral of the previous type for scalar functions. Do you agree? But that's not what we want. We want somehow to be able to calculate this thing. And let's see what we get. So here is... So first of all, this we know we can write in terms of the parametrization. So what we're going to write is the integral from a to b dt. And we know that r prime of t shows up here. Right? I'm writing it by the definition of a... Let's write this here. This is a line integral of a scalar function. Okay, so we know it equals the integral from a to b. The ds becomes r prime t dt, and then we have the f dot t. Okay, but what is f dot t? Let me remind you that f dot t is, I'm going to replace t. What was t? T was the normalized tangent vector. What's the normalized tangent vector? The tangent vector is r prime of t. And normalizing it means we're dividing by its length. Do you agree? This is t. And then I'm doing r prime t dt. And this is a scalar. I can pull it out of the dot product and cancel it out with this. Do you agree? So what I get is the integral from a to b of f dot r prime of t dt. Clear? And this is the definition. This is what we want to formally define one. So this was kind of the motivation, how this arises, and this is the definition. So let's write it. Definition: the integral over gamma of f, and now f is a field, which we indicate by this arrow up here, and usually we use capital letters, dot dr. This is the notation. This is meaningless. You can't calculate anything with this. This is just a notation, just like the integral of little f ds was just notation. But what is it really? It's the integral from a to b, f of x of t, y of t, dot r prime of t, dt. Okay, so this is what it really is. That's what we found out there. Is called the line integral, or is the line integral of f over gamma, where gamma is given by the parametrization r of t, where t ranges from a to b. Okay? It's also written so we can extend what this means. So what is f of x of t, y of t? Integral over gamma f dot dr. Okay. So by the way, do you understand why this notation? So I'm taking f and doing dot r prime t dt, right? Dot r prime t dt. So if you think of r prime t, if you think of this as dr to dt, dr to dt, then what's written here is f dot dr over dt times dt. Cancel out the dt's. This is just notation, right? So that's the reason for this name, f dot dr. Clear? You understand why it's written like this, why this is kind of indicative of what it really is. Clear? Okay, so let's open it up. So what do we have here? We have the integral from a to b. What is f? F is a field. It has two components, p and q, right? So we have P of x of t, y of t. We'll do an example in a minute. And P in the dot product meets the I component of R prime. What's the I component of R prime? X prime. Right? R was x of t, y of t. R prime is x prime, y prime. Do you agree? Good. Plus the j component of this, which we called q of x of t, y of t, meets the j component of R prime, which is y prime. And then all of this dt. Clear? So let me write up here. So f, let's do it in a different color and do it on the top. So let's write here. F is p comma q, and R prime is x prime comma y prime. So f dot R prime is p times x prime plus q times y prime. Do you see that, everybody? Clear? So this is as explicit as it can get. This is what we actually calculate in an example that we're going to do in a second. And this has another symbolic notation. We write it as the integral over gamma of, look what we have here. We have p times x prime, and remember that x prime can be written as dx over dt, and y prime can be written as dy over dt. And for the same symbolic reasons used previously, x prime dt is dx over dt times dt, so it's often written p dx plus q dy. This is, again, just notation. You can't do anything with this. It's just notation. Convenient notation. We'll use it a lot, and it's used a lot. Is it clear why? Why this is the notation? Why this hints that what we're really looking at is this? Clear? So this is the line integral of a field over a curve gamma. Let's do an example. The example that we discussed for the line integral of a scalar function was the helix. Let's do the helix again, but now in a totally different context. So, example, f of x, y, z, the field is going to be given by x in the I direction plus y in the j direction plus z in the k direction. Do you see that this is a field, that its output is a vector? What's q of x, y, z for this field? Q is the j component, so q for this field is just y. This is q. This is q of x, y, z. Okay, it's a simple field because it's the first example, so it's a simple example. And this is r of x, y, z. Again, I'm doing straight away an example with 3 variables, although everything we wrote was for 2, because it's easier to write for 2, but it's exactly the same thing for 3. Do you agree that this is a field? Okay? And gamma is going to be the helix. Gamma is the helix given by cosine t, that's right, r of t equals cosine t, sine of t, t, where t ranges between 2 pi and 0. Okay? What is the work done by this force in moving a bead along the helix between 0 and 2 pi? one round of the helix. Do you understand why I'm doing this? Good? So the work of F in moving a bead along gamma is what? It's the integral of F dot dr over gamma. This is just notation. It's nothing we can really work with. But what we can work with is we have to calculate all the details that we had. So it's going to be the integral from a to b, 0 to 2 pi, of f on gamma, so f on gamma, it's going to be a vector. So this is f of x of t, y of t, z of t. So what is it? Well, it's a very simple field. So x of t was just x, so it's going to be cosine t. Sorry, p was just x. I'm confusing you. F of x of t, y of t, z of t has three components, p, q, and r, right? P was just x. X is cosine t. So it's going to be cosine t. Q is just y. Y is sine of t. So we have here sine of t. Z, r is just z, and z on the curve is just t. So do you agree that this is the field calculated on a point at the curve? Dot r prime. What is r prime? Minus sine of t, cosine t, 1. Do you agree? Okay, so this is the field, and this is r prime. And then all of this, we have to integrate dt. Clear? Okay, what do we get? The integral from 0 to 2 pi minus sine t cosine t plus sine t cosine t, that's 0, plus t. Simple example. Okay, we're going to do more intriguing examples later. So we get t squared over 2 evaluated between 0 and 2 pi. So we get 4 pi squared divided by 2. So we get 2 pi squared. Questions? Is it clear? Good? Okay. So let's give a big box to this formula here. It's all in between lots of tiny remarks and things like this. But this is what we really want to remember. This is the definition of the line integral of a field over gamma. What we should remark is that, oh, there's an important remark. So 2 remarks. Let's write them. First remark is that it doesn't depend on the parametrization. That again is something that requires proof. It's not something you can just look at and say, obviously it doesn't depend on the parametrization. It requires proof, but we're not going to do that proof. So remarks. 1, the integral of f dot dr does not depend on the choice of parametrization. This is almost accurate. It's not entirely accurate, and making it accurate is the remark, the next remark. So let's write, does not depend on the choice of parametrization, except it does depend on direction. Okay? So you can choose whatever parametrization you want, but the work going from point A to point B is not the same as the work going from point B to point A. Okay? In fact, the work going from point B to point A is precisely minus the work going from point A to point B. Okay? But it does depend on what is called the orientation of the curve. Okay? On the direction of the curve. Orientation. So, if, suppose this is gamma, this is a curve gamma, some curve, gamma has an orientation. We're going in this direction. We're thinking of it as having an orientation. The curve going the other way, so the exact same curve, and of course I didn't make a simple thing that I can easily draw again, but let's give it a shot anyway. Okay, so this, when going the other way, this is called minus gamma. Okay? Going along the same curve in the other direction is denoted by minus gamma. Okay? And the work depends on which way you're going. Okay? The work is assigned. It's not like like mass. You don't have a thing as negative mass, or the area under the fence is no such thing as negative area, right? It's the area. It doesn't depend if you're counting it this way or that way. Do you understand the weird movements that I'm doing? Okay? So for the work, it does depend. There can be a negative work. Okay? So the integral of f dot dr along along minus gamma doesn't equal the integral of f dot dr, the work along gamma, but equals minus the work along gamma. Okay? And again, that's true for any parametrization as long as you're consistent with the directionality. Okay? So if you take the same parametrization and look at it once as t going from 0 to 2 pi and the other time where t is going from 2 pi to 0, you'd get a minus. Okay? Clear? Okay. So we'll do more examples. This is just the beginning. This is just the introduction. We'll do more examples of calculating line integrals in the next clip, and we're going to start discovering some phenomena related to line integrals, which are going to lead us to some more theory and more notions like Green's theorem and like the concept of a conserving field and so on. So that's coming up next.